record like with two computers, so it's very safe. So oh, I have some echo. Let me turn off the mic. Okay, so we really started to talk about like networks today. So so far like we talk about SVM and so on. You can think of a really a neural networks with only a single neurons. So now if we have like more neurons and form a layer of kind of like networks like this one, then the question is like how we are going to train the network. Right? So we're given like some training data here. Like again, I start with something simple, is supervised learning. So we have some expected input and then some anticipated output. So we want to kind of like fit the parameter such that like given the inputs will give us the desirable output, right? So and in more detail, so like let's say more precise, let's say I have like input with a dimension d in here, and the output let's say is a or have also this time it's not a scalar but like a vector with dimension d out here. And then, oh, wait a sec. I need to make sure I pull your chat. So wait a sec. Chat here. Yeah, okay. And so if I'm doing linear regression, so basically we just want to fit a linear model. Right? So we have this function that we're trying to fit in with parameter w. So it would be something like wx, right? There's some bias here. Here, just for simplicity, I just say wx, right? Let's say we absorb the bias somehow. And then like now if I create more layer, okay, before that, let's say to determine whether we are doing a good job or not, then we may have y hat is like uh, the desired output, that's the training data that we expected our output is y hat. Then we can compare the difference. I just compare, let's say the with the L2 norm to see like um, the mean square error to see if like the our desired output is like far from the output like generated by the current parameter. So okay, yeah, that's the loss. It's very simple. Now, if I create a new model here, let's say to create a little bit more complex model, let's say I have like two W now, like W1 and W2. So I have the new model is a matrix multiplication. Okay, I guess I start with like a question to check like you guys are following what I'm saying here so far. So will this is the difficulty using PowerPoint. I cannot write that, right? Can I type test here? Maybe let's see. No, I don't think so, unless I get out of the slide here. But okay, let's say so. A question here is really kind of trying to train my super mouse skill here. The question is like, will this model like here be? Do you expect like for this model you get like I would say like it's able to fit better than this model here. So now it's or like I put it another way, like now I have like two W here. Does this model like provide a better potential can better fit with the training data X and Y? So this is here training data like X and Y are here. Then this kind of like generic linear regression model here. Okay, someone give a very quick answer for that. But yeah, you have to be careful. Yes. Uh, so this is some of these cases. I actually the majority is wrong. So here, here, I know that like because yeah, because like I have this W1 W2, they are linear. Think of like okay, if have a model like that, like what is this W1 W2? I don't care what is W1 W2, but it doesn't add anything additional compared to this model here. So anything can be modeled by this. I mean, anything model can be modeled by this new model, can be modeled by this old model as well. Because I think of any W1 and W2 here, when multiply them together, it will be some kind of like, let's say W tutor. I can simply set W as W tutor or like W as W2 multiplied by W1. I would essentially have the same model here, right? I don't have anything additional. So therefore, like in this case, no, actually, you don't get more out of that. But you will get more if I introduce some nonlinearity in the middle, basically instead of like just W1, W2 multiplied by W1. Let's say after I multiply by W1, I kind of apply an nonlinear function here. That's basically the activation function. So maybe like sigmoid, even step function, and then multiply by W2. Now in this case, like this guy here, W2 sigma W1 here, like we cannot model by any of this W here anymore. So it offers something extra basically. So therefore, like in neural network, like it doesn't matter like how many layers you have, like here. It's important that if you don't add any nonlinearity in the model here, it doesn't do anything, like no matter how many layers you have. So it is the nonlinearity in the middle that actually add the additional complexity there. So so therefore, like we need to have activation function, and we'll talk a little bit more later on. Just so maybe like some very common nonlinearity, let's say well, like I will mention sigmoid also like earlier. Um, and so this is like with we have one layer, like we have this one layer model here, right? We just add one layer, we have sigma, and then like W2 here. Now I can have more layers like this one sigma. I can do a W1 multiplied by W1 first, and then I have like activation sigma, and then multiply by W2, and then have another activation. I can have like same activation function, or I can use different activation function. I can have like both of them like value, or like I can use different things like maybe one is value, one is sigmoid. Right, that's totally fine. Um, then the problem now is like the entire problem is I just go back to here. Is like we are trying to find the best W to fit our data here, such that this loss function is minimized. So therefore, it's really an optimization function, optimization problem here. So as we see again, basically we have the entire picture is like this, right? We have this function, we have this model, this W will be all the ways here, right? We have like lots of layers here. I can have like different ways here. And this is my prediction. And I will specify some of the loss function, specify a loss such that my outcome, predicted outcome should be close to the desired outcome. And of course, I need to, once I decide uh, determine what model or like, yeah, whatever order you want to have, actually, most likely you should collect your data first. Assume I already collect the data, have for the supervised learning, I need to have like, for each um, given training data sample, I need to have the corresponding like label, the ground truth there, like for the Y there. So I have like a pair tuple here. I have a couple like for n samples here. Let's say this is my training data. Then I determine the model. Then I determine the loss function. The loss function can be, as I mentioned earlier, can be just like square difference, let's say. Uh, then this will be my risk. Sometimes people do the expected loss or risk. Sometimes like whatever you call that. Then we're trying to minimize that, right? For all of the sample, like some over take the average of them, like for the training samples to be as small as possible. it's also possible that we want to add a regularization term. Like actually we mentioned also earlier, I guess, that like let's say we can add L2 or L1 regularization in linear regression. We mentioned that. This is basically used to kind of like um, try to like avoid this model getting crazy, like overfit. So it's like to penalize like overly complex model. So then that's it. They become like really an optimization problem. We're trying to minimize this. So the question is like how to optimize this, how to find the optimum W with like this xi, yi fx, like, and how to solve this optimization problem. So okay, before I get to that, like let's see like what's the difference like, of uh, let's say deep learning from whatever we have like before like deep learning. So machine learning have been used to solve lots of the classification problem or like problem that cannot handle by algorithm like for a long period of time. So as you mentioned like, earlier, I guess like, at the beginning of this course here, I mean I guess probably in the first lecture, we say some of this problem is very difficult to solve by classic algorithm. For example, like I can have a sorting problem is you can lay out very precisely how to do sorting. For example, you have a list of number. If I try to sort, just use the simple sorting algorithm. Let's say I can do bubble sort. I can look at a pair at a time and determine which is bigger. And then if one is like bigger than the other one, I swap it. Otherwise, I don't swap it. Stuff like that. But if I try to classify images, it's totally unclear how we are able to write a program systematically, able to classify apple from oranges, let's say. So therefore, we need to look for a data-driven approach. So the approach before deep learning will be something like engineer trying to figure out some features. For example, like I'm trying to handle like image classification. So they think of like different features, like maybe like edge features, like or texture, or like maybe local feature like sieve and so on. So once they determine a bunch of features, they pack them together. Now then they create this a list of features, and then they try to train a classifier to classify the model. So again, you will have this training data, training samples. So you still need to prepare the data. Basically, you have like in this case, like for example, like I have like images of apples, images of bear, pear, pear. How do you call that? Or anyway, and images of I thought it's orange. I guess it's more like tomato, and so on and so forth. And um, and then like you have all of these images. For each of the image, you compute the feature, right? You have this decide what kind of feature you're going to extract the image. So if you have a procedure here, you just for any input image, you just create a vector will be the feature, and then like given this feature now, you know also what object you're looking at, right? What is the subject, right? So then you know the label. Then now you just have like given x and y. Now you train the classifier basically. Then once you train the classifier, when you evaluate, do testing, you just have an input, and then again you extract feature from that, and then from the learn classifier you get the prediction, you get the label whether it's orange, apple, and so on and so forth. Now this is like people have been doing that for a long period of time and has been kind of like reasonably successful. Like this has been done like up to like 2012, you can say, like for computer vision. But since like 2005, 2007, like people actually like researcher on neural networks have lots of progress, right? They're able to train like deeper network. Actually, even that, like even 2012, before 2012, for example, if you look at Yang Kun, they have here's the early work like for digit classification, for like handwritten digital classification, and that's been done in the 90s. So using neural networks, even though like it has been forgotten like for a long period of time. So I mean, in that case, like, he also used a little bit deeper network. So also like not very deep, but reasonably deep. So but for deep network, for deep learning, oops, where am I? For deep learning, so the thing is like the difference is like we are doing end to end. So for before that, like we human and engineers are involved to try to design this image feature extraction procedure, right? But here instead, like we just leave everything to the machine. So actually, we can do. Of course, you're thinking like, oh, why can't I do that? Like even before we're using deep learning. So the problem is that if you're trying to train SVM with this, that will be like an image will be really large, right? So an image, not even high resolution image, just a regular image, let's say 200 by 200, you have like 40,000 features, right? So it's doable, but it's actually quite large and you won't get good result. Like you don't have sufficient data and so on and so forth. Like um and and and, and it won't do as good like with that kind of like uh basically with that kind of like model capacity of amount of data and so on, you won't be sufficient just doing without this feature extraction step basically. So but with sufficient data and also like with increase of model I mean increase in like computational power and also like with some additional trick doing like deep neural network training. So now we're able to have a much complex model or like complex model meaning that I have like more layers. So then like you can imagine like we have the earlier layer actually trying to generate features and and the later layer is doing the classification. So the feature generation step is also kind of become data driven and is handled by the neural networks. So for example here like we have training this let's say an example like training a deep networks. You can see if I visualize like the feature at different layers, you can see that the earlier layer, the feature is very much similar to if you know a little bit image processing like Gabor filter, like um, that kind of trying to extract edges, patches, and so on. So this is kind of similar to this low level feature generated, kind of like hand engineered by wavelet, Gabor filter, and so on and so forth. But as you go into like deeper layer, you have like more capacity. Say uh, you have like features like actually if you look at this here, you can see like even like this layer, you get eyes and so on and so forth. So so this is one interpretation. Even though like nowadays I also you may not want to take it too literally, thinking that like each of this layer will correspond to like you expect that really will each of the layer you will be able to extract like some features. It may or may not be possible, depends on the network you're using, but this is a kind of like a good analogy or a good metaphor like what's going on. Um, Now okay, go back to the optimization problem here. We have the again, this is basically a loss function with the regularization. We have just have this as a function. We're trying to optimize that, right? So we can do okay. Well, how do we do optimization? So that's unless for very few cases, for example, like for linear regression and so on, it's impossible to get a closed form solution. For almost all other problems, you are not able to solve in closed form. So you can do a random search or like maybe a convex optimization will help. Um, of course, random search is pretty crazy, but even convex optimization like is kind of not very easy in a sense like um, because of the number of parameters is involved. For example, think of like GPT-3 that involve like hundreds of billions of parameters. So it's a scale that like it used to be like people saying a million parameters. Like how can you handle like optimization with a million parameters? Like people is thinking like typically the number of parameters they can handle is like a lot more than tens of thousands basically. But nowadays, like people are trying to look at these problems. I have like close to a trillion parameters. So, and then best way, like, oh, I shouldn't say the best way, but the way that usually in those cases would be like just doing gradient descent. So cannot think of like a good way. So you can think of like this is a um okay, for optimization problem you can think of like it's like going downhill in the landscape. So then the gradient is essentially just pointing you the direction going uphill way. So if you have the gradient, you should just go to the opposite direction to go downhill. So then therefore you have the so-called gradient descent uh, kind of approach, or you heard of like something like stochastic gradient descent, batch gradient descent, and so on and so forth. We'll talk a little bit more for those optimization, but today we'll focus on like just okay, how do we find the gradient? So um, even for okay, here is an example gradient descent here. So if I know the gradient here, then I can simply going into the opposite direction, right? So I will have this alpha here known as the learning rate. I'll just say kind of like change my W, update my W as like kind of like decreasing the gradient, kind of decreasing something proportional to the gradient. So if you have the learning rate to be bigger, alpha is bigger, then walk you go for a larger step. If the learning rate is smaller, you go for a smaller step. And yeah, okay. And this is also only one way of update rules. Like you can have like more involved um update rule for different optimization. We'll talk a little bit more for that one, as I mentioned. So this is an illustration like for different update rule, like different kind of like we'll talk about that later. So now the how do we compute gradient? So of course, we can do it on a paper in some sense. For example, like we know we have this optimization problem. Okay, basically we have this objective function with variables like W1, W2, W3. I say these are the parameters we're trying to tune, right? So therefore they are the variables here. So we want to find the gradient with respect to like W1, W2, and W3, right? So the problem is that as you go higher, like maybe even 3 layers is manageable, but you have like for example Westlet is like typically over 100 layers. So it's not hard to find like neural ledgers with more than 100 layers nowadays. Like so therefore it's basically impossible to do this like by brute force. So luckily what we can do is like we can just take advantage with like what we learn in calculus in high school, or like maybe not high school, maybe in your first calculus class. So you know the train rule. So basically oh, sorry. Yeah, it's okay. So we have this train rule, right? For example, if I need to take derivative, let's say I have a x is a function of like w itself, or like or let's say yeah f. Let's say I have actually f. What should I say? I have x. Then x is go for a function to get w, and then let's say function g to get w, and then w will go for another function h to get uh let's say L, let's say whatever. This is like my final loss, and I have this here. I can think of f, right? So it's a function of x. So I want to know like what's the how it changed. Like basically, I have L, so therefore it's equal to fx. How my L change with respect to x, right? So it can be then we can have chain rule. Okay, can you fill in the blank here? Oh, okay, maybe I fill one more. Uh, okay, maybe I write like this first. So the partial L partial X is actually equal to partial F. x partial x, right? So it's equal to partial L partial I don't know. I mean, like that's very silly to try to make this question here. So what's this guy here? Maybe put it that way. Just wait a sec. Oh, okay, that's fine. Okay, yeah. Um, yeah. It's so silly. I'm trying to create a question, but I guess it's, but just so, but what's partial L, partial H, partial X? So L is function of H, right? So it says partial H W, partial W here. And this is a let's see, partial. Wait a sec. I'm thinking like whether I want to have this. This is of course this is correct, but I'm not sure this is what I want. Let's see. Partial G x over x. Right. I have this here. So let's see. I I want to find this. What I'm propagate back is yeah. Okay, that's fine. What I propagate back is actually first I okay first I okay this is actually this is also partial L partial W actually maybe it's don't write it well just write this here. So then I have this propagate back here. First is I know what is how my gradient change with respect to W here. Now if I want to see like what's the how my L change with respect to X, I can multiply this guy with the local derivative here of the output of G with respect to the input X here. That's partial G X over partial X. So or like partial W over X here. So okay, let me repeat that. Just make sure that I. So here's the picture again. So I have, let's say I have like function, I have some parameter x and y, right? So what's going on is like when you're doing a forward pass, you are okay. I mean, like first you're trying to evaluate like something where you have the input, like you have the input, and trying to evaluate the output given the current parameters. Then, so let's say I input x and y here for this particular node here. I have output c here, and then I keep going forward. Maybe just wait a sec. I guess what I want to say is maybe I copy this. Oh, actually, this slides right. This cut. Yeah, maybe I. So what I mean is like, so the procedure will be more like that. Like I just make sure that like I talk. I mean, um, you're following the entire procedure. So I have this, like let's say like training data like xi, let's say x1, like some sample, like just take one sample at this time, like so just take one sample at a time. So I want to, I go forward, right? So I go forward, I get evaluate to this y here. Let's say I get y here, y hat here, or y just call y here. Now my y should be close to y1, right? So then I compute the loss, right? The loss is like y minus y1 somehow. And then I compute like what's the partial derivative of L with respect to y here. And so let's say if like my L is like just L's just like square loss. So let's say if like my L is equal to L, let's say L y is, I want to write it here. So L is a y minus y1, let's say. And this is called L, let's say. So what's partial L, partial y here? Okay, this is a question. What's partial L, partial y here? I cannot see your chart. I need to put this back. So I have this output here is y, right? And then I have my design output should be y1. And let's say I use a square norm to estimate the loss here. So what's partial L, partial y? How do the loss change with respect to y? From this example, of course. Yes, you just take the derivative, right? Take the derivative of this guy, then will be like 2y minus y1, right? Yeah. So now this is my partial L, partial y. What I'm interested in is like this have like lots of ways in here, right? That's way one, way two, right? I'm interested in like partial L, partial W1, or like even like maybe I write like this, like the maybe I write like 1, 2 like here. So maybe I'm interested in, or maybe like do not use, maybe I have like this is W, like weight W, and then I have another weight like W tilde, let's say. So I'm interested in like for each of these element, right? Partial L, partial Wij. So I know like how I should change the weight like for the Ij element of this W here, right? Now to, or like of course I okay. I mean just write this shorthand one, like just shorthand notation. So partial L, partial W. But you understood that this is actually a matrix. Yeah. If your W is a matrix. So and now, and if I need this partial L, partial W, right? Maybe W tilde here, right? Then that can be like partial L, partial W. Let's see, I already used it. Partial L, partial W tilde here can be like partial L, partial Y, and then partial Y, partial W tilde. Right? And Y is basically here. Let's say Y is equal to W tilde. Maybe I have an intermediate input here called Z here, W tilde Z, right? So then here I know what is this, right? Then I would have this one here. By the way, do you know what would be this one here? If I have Y is equal to W tilde Z. Oh, actually, this is a little bit complicated, maybe. Yeah. So maybe I will assume we can assume y is a scalar first. So y is a scalar, then W tilde here should be just a vector here. So and more appropriate may write like this actually. Then like partial y partial W tilde is just z, right? This is just z actually. So then when I kind of like trying to pass back pass back the gradient, for the backpropagation, I will first say, okay, once I going forward, I get this x value, I get this z value, I get this y value, right? Then I pass back the gradient. I compute this partial L partial Y, so I know it's this guy. Then for each step here, I should multiply by the current, uh, the local gradient with the gradient that fitting back. That basically is like this partial L partial Y multiplied by this partial Y partial 2 W tilde. Okay, so okay, I will give more example. I guess it is a little bit confusing here, but let me look at this picture here again. So, and then, oops. So here again, I'm showing a scalar case. When this scalar case is very obvious, right? So you have like this local gradient is when I go first, I think of like what's the procedure of the entire thing. I should have like going forward, like I have like values starting from giving the input, and this is like passing for one of the new one. I have the input x and y, I get output c, and then c will continue to go to the next layer and so on. Now, when I going backward, and by the way, at the same time, actually, at this moment, we can compute the local gradient as well. That basically the partial derivative of the output of that new one with respect to the input. And we can store it. Typically, that's what's going to happen like in the actual implementation of this packages, like PyTorch and TensorFlow and so on. They will also at the same time store the gradient when they're doing the forward, like at the same time. And when you go to the end, then you compute the gradient, uh, like with respect to the output. Then you pass backward. Like for example, like it continue to pass backward, and then you have the gradient of L with respect to Z here. When then for this part continue to pass backward, it will just have like this partial L power C multiplied by partial B partial X and so on and so forth. So conceptually it's very simple actually. But let's see if let me give an example, like more kind of complete example, I guess. So let's say if I have I have just like a again a similar to model. Like, let's just use a linear model like as an example, linear regression. So I have, let's say I have x coming in. This is a vector. Let's say this is a vector here. X coming in, and then it will go for some weight. Now the weight it can be varying, right? So let me put here like some w here. So and then like they multiply together. I have like this output here is, let's say I call it q here is equal to wx, and then okay, and then simply I have some desired output, maybe call it q tilde. So, and I want this q tilde to be close to q. So I compute the L2 norm of that. So the L2 norm will be just equal to q minus q tilde, let's say. So to make it more realistic, let's say this time q is a vector in general. So therefore like w in general is a matrix. And So Q tutor is also a vector here. And then, okay, maybe just ask some question here. So I have like, this is I can call this is loss. Maybe I call this is L here. So when I pass back the, okay, when I go forward, of course I have X coming in, then I compute the corresponding Q, then I compute the corresponding L, right? And then when I go backward, let's say I have this first here, I will have like partial L, that basically just a trivial one here. And then I can think of like the next one, partial L, partial Q is equal to partial L multiplied by partial L, partial Q. It's a little bit redundant, but that is just equal to the, okay, actually that is just equal to, actually we already have that, that is just equal to, we asked that earlier, it's just equal to 2 Q minus Q tutor here. Now for partial L, partial W, what we're interested in, that will be equal to partial L, partial Q. So I have this partial L, partial Q computed. So you can think of like this, it's like fitting back like something is redundant, it's just a partial L is equal to 1. Now multiply by the local gradient, that is partial L, partial Q. I guess partial L, partial Q here. Now then when I pass further back here, I should have partial L, partial Q multiplied by partial Q, partial W, right? So partial L, partial Q multiplied by partial Q, partial W. So, okay, let me give something like precise. And so let's say I have X here, it's just equal to 0 0.2, 0 0.4 here. And my W is a 2 by 2, let's say 0 0.1, 0 0.5, minus 0 0.3, 0 0.8 here. So first question, what's the dimension of partial Q, partial W? Brandon try to answer. So yes, it's actually a trickier question than you first look at, maybe. I mean, the problem is like when we write, this is a very everyone might like this, honestly. But at the same time, like, this is actually miss out lots of detail here. The intuition is actually indeed is like this, but but you remember I said something like at one point that the gradient, yeah, I guess I abandoned got what I said, but like it's not in this case that does not apply here. It's like the gradient is it should have the, basically if you have like some function here, let's say I have like some x vector, let's say x here, and if I go for some function f here and got y here, and y is a scalar here, then the gradient of fy or like of y or fx with respect to x should have the same shape, same dimension as x itself. So let me, this dimension here should be equal to the dimension of x. So otherwise it doesn't make sense, right? Because the dimension here, think of like when you do update, you have x is going to go along to this dimension, this go along this gradient, right? So if they are not the same, basically what I'm saying, like we are doing update like this, right? X minus alpha gradient of f, right? So if these two are not the same dimension, it doesn't add up, right? But know that like this is only the case when like the output here is a scalar. When this is a vector, you should think of like what happened is a vector. Then like, let's say if I have a vector function, I cannot go down further. Can I? Can I? No, I cannot actually. Okay, I will just copy then. Maybe copy this thing here. Okay, so if I have a vector case here, so if I have x here, I have function f, but I get like some function vector like maybe z here. This is also vector. So what's going on is that you should imagine that like you actually have something like this. You have x f1. Yeah, go for f1. You get some c1 here. F2, you get c2 here. And maybe just 3 cases here. F3, c3 here. So let's say this c is equal to c1, c2, c3. And now this will go back to this case here, that the gradient of this c1 with respect to, or like the f1 x with respect to x, this should be have the dimension, the same dimension as x, because this is exactly the case here, right? And this guy also has same dimension of this one here. So therefore, overall, like what's the dimension of this together? Then will be 3 times in this case, in this special case here, will be 3 times of the dimension of x, right? So in general, your dimension of your local gradient should be the dimension of the input multiplied by the dimension of the output. So therefore, in this case here, the dimension actually for this guy should be like equal to dimension of W is 2 by 2. And then for Q, I have 2 dimension as well, because W multiplied by X is a 2 by 1 vector, right? So I have 2 dimension for this guy also. So therefore, like the whole dimension is 8. 2 by 2 by 2, 2 by 2 by 2. Yeah, 2 by 2 by 2. Yeah. So, but then if you think of that, so how we should interpret this multiplication here? So that this multiplication that people just write down should be interpreted when Q is a vector, should be interpreted in the sense that like I have this is equal to partial L partial Q1 partial Q1 over partial W plus partial L partial Q2 partial Q2 partial W. And this is exactly the case when you have chain rule, right? So you have chain rule that you have L depend on W and W depend on parameters like Q1 and Q2, right? So therefore, like or like I should say like L is connected to W like for two variables like Q1 and Q2, right? So therefore, like we should like add these two together, right? So if you interpret that way, this is like very, very natural then. Like that's just something I want to kind of I guess it's a picture that is a best way to uh, kind of like keep that in your mind and like understand like what's actually going on. Because like people typically write this down, then when you think about it, you don't even know what's the dimension. Like many people then when they were asked like, what's the dimension of this local gradient, then they don't know actually. They don't even know. So that actually you yeah, it's good you pay attention to that. And that's it. I guess I will let's see if I should yeah, maybe I show the slides for this one here. So so I have like say have like these numbers I just given earlier, right? So doing forward, I give this number here, right? So I multiply, I get this Q here. Now then I'm supposed to compute the L, right? So let's say I compute, oh, okay, I didn't write down the L, but let's say the L is some number here. Now going backward, then oh, okay. By the way, yeah, it's okay. When I compute this one, like I should compute the local gradient as well. And the local gradient, as I mentioned, like the dimension will be, I have two values here, right? So therefore, like I essentially have like two matrices here for the partial Q, partial W. So one is like for partial Q1, partial W, you can think of. The other one is partial Q2 with respect to partial W. So therefore, I have two matrices here. So also like for partial Q, partial X, I actually also have like 2 by 2 as well. So you can think of this as a partial Q1, partial X, and then partial Q2, partial X. Right. So, okay, you can see it, but I want to, yeah, that's fine. Okay. I'm thinking like whether I should ask you like to what are the numbers supposed to be, but I show you already. But do you remember that? Do you get, can you get that back? There was partial Q, partial X. Do you oh, okay, that maybe is a good question to ask then. Like you should think a little bit about it. What's partial Q, partial X? Let me get back to the Suno here. Maybe I can put it side by side. So even though I showed it earlier, I guess you guys don't have photographic memory, probably don't aware of don't. Okay, what's partial Q, partial X here? Know that I have Q is equal to WX, right? Yes, it's W, but actually how that put together will be I have but I put it in the sense I put it as two vectors. It's easier to understand because that will be correspond to gradient partial Q partial X in two terms there, partial Q1 partial X and partial Q2 partial X here. So partial Q1 partial X will be just, let's say, will be okay. What will be this one actually? Maybe I even ask like this. I have this number here, right? So there's two ways to put in this number, I guess. So what is this one? Like just for the first one. My question. Okay, yeah, yes, 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 yeah. I guess you're yes, you're right. I think you're right. So yes, because you think of that like Q1, you split that Q1 Q2 is that you have this matrix like 0, 1, 0.5, right? And then like x1, x2, right? So these are the variable correspond to contributing this Q1 here. And yeah, partial Q and partial X is actually this two, yeah, two parameter here. So say 0, 0.1, like this. So you store the local gradient here, and then you continue to compute and compute like what's the output of L here. Let's say is equal to basically L is like equal to this guy, right? Here I think I just set Q tilde is equal to 0. So then I have L equal to this guy. Now then I going back here, I have this partial L partial Q. Yeah, actually I also compute partial L partial Q here. That will be, I mean, when I do the output, I should also like compute the local gradient as well. So then I finish that. Then the entire forward finish. Then I just feedback starting at the very end. This I have this one is just a dummy. It's a partial L multiplied by the local gradient. Then will be like 0.44, 0.52, and so on, right? Now then continue to go back here. Let's say if let's see which direction I'm going first. Uh, let's say I go like this. Now I need to, I have this is like going back, right? I want to compute partial L, partial W. So what would be the partial L, partial W here? It's a little bit, maybe just the first number of the partial L, partial W. What I mean here is like, that will be, give me partial L, partial W will be four numbers here, right? So let's say just what is this number here? From the value, I'm going back, coming back like the gradient is this one, and the local gradient are these guys here. Wow, that's a okay, yeah, that's yeah, that's very good, yeah. So yeah, so you have like partial L partial W should be equal to partial L partial Q partial Q partial W, right? Partial Q partial W is the two thing here. But again, like if you just write like this, you don't really get. I mean, like you can be when you really want to know the detail, it probably like you will get you are not able to really figure that out. So this is actually really mean like partial L partial Q1 partial Q1 partial W plus partial L partial Q2 partial Q2 partial W, right? So and so I have this partial L partial uh, Q1 is just 0.44, right? This is 0.44. And partial L partial Q2 is just 0.52. And I have Q1 partial W is the first matrix here, like 0.2, 0.4, 0, 0, and then maybe it's better to use different color. Yeah, and this is a the parcel Q to parcel W is a 0, 0, 0.2, 0.2, 0.4, right? So therefore, you add this together for the first element will be 0.88. Yeah. So and that's basically, yeah. So and maybe one more example here. I guess it's better for me to open the file directly using Zuno, and then I don't need to okay. So wait a sec. My mouse disappear. Okay, here. Okay, let's try a softmax example. So if we remember, I guess we mentioned that like earlier, then if you yeah, actually pretty early when we talk about logistic regression. So when we do classification, then when we have multiple class, then we can use softmax, right? So basically, if we try to do classification, we have the output here. Let's say you have like several layer. Let's say I have, yeah, I can maybe just draw like this. So I have some input X here, go for several layers here. And then I have like classify into three classes, let's say cat, dog, and pig, let's say. And then like I want to get a probability, so I try. This is like just score numbers, right? The higher the score is more likely to be. For example, the cat score is large, and then it's more likely to be cat. Then to transform into probability, so we are going to do softmax, right? So we just have this score here. Here in this case, we call it O here. We just like I have the old cat and old dog, and then like old pig, let's say. Then I just do an exponential of them, each of them. Then I just normalize them. So by dividing the sum of these exponentials, so that would be a softmax. So now I will have the output of my cat, dog, and so on. My cat, dog, let's say I have, this is a one. Let me in this here, like maybe just see if you guys remember like some of this stuff. So let's say okay, this, sorry, let's say O is, yeah, I use the same notation here. This is actually not very nice. I have this called O here. I'm use O again. Uh, oh, okay. I call it sigma here. I thought this is O. That's fine. So and then afterward, like this, I got the sigma is my softmax. Let's have sigma C, sigma B, and sigma P. I say, and then let's say my cat score is a 0.4, and then my how is supposed to be dog. Dog score is a 0.5, and then my pig score is 0.1, let's say. And let's say the ground truth is actually a dog. You're doing correctly. And reduce cross-entropy loss. So do you know the value for that? Like this is a question that trying to see if you remember like what we talk about, like you know cross-entropy like in general. So the ground truth label is dog in this case, and the probability from softmax is 0.4, 0.5, and 0.1. So then what's the softmax? Sorry, what was the cross-entropy loss? So you guys are flipping. Okay. Uh, Not quite right, but it's a good guess, I guess. Um, Probably not right. I don't know. Like the uh, so any other guess? Like not guess actually. If you can, you can even flip through the earlier slides or like something like or like see if you can just wiki and find the definition of cross entropy loss. So remember like, the cross entropy loss where coming from is like really the trying to I have like these two, like this is like my estimate. Let's say this is my sigma is like has a distribution, right? This I can think of this as a distribution, and I have my ground truth is like this, and I want to make sure these two are close together. It well, this is a bit fake, like so. But I have this value here. I'm expecting you give the precise value in this case, um, too. So and this we can compare two distribution whether they're close or not, typically using character divergence, right? And if you remember, like basically the cross entropy loss is just, let's say if I have this uh this ground truth case, if I call it Q here, and this probability distribution I call it P here, then the what we are doing is I simply trying to compare the character divergence. When the character divergence is equal to 0, then Q is equal to P here, then we are doing a good job. So the loss is equal to 0. And this only happens like when P is precisely the same as Q here. So look exactly the same. So in this case, these two are not the same. And the character divergence is something like sum over this Q for different classes here, log Q C over PC here. And I have this C can be like classes is dog, cat, and pig. Okay, I have the two C here, but you guys know this C is different than our C, right? So maybe I put a C pi here. And then like, of course, my Q here is actually a delta function. It only happens for the dog. So therefore, this is actually just equal to log 1 over P C P dog. So, or like this is a sigma D. So therefore, it's a log 1 over sigma D here. So you can use different log, like you can use either like lateral log or like base 2. If you use base 2, then maybe get 1 bit, right? Or like something like that. If you use yeah, or people typically ignore the unit here. Or if you use lateral log, you will get something else. But okay, that is the cost. Let's assume lateral loss. This is it won't be equal to 1 if I use lateral log. But let's use lateral log here for the derivation for the for backpropagation because it's easier. So let's look at the derivative. Like when let's say if I have this, in this case, like I have a classifier here, I have softmax, right? I'm going for softmax. So let's say I have some output here, I call it O here. And then I go through this softmax layer. And I got sigma here, as I mentioned, this is sigma here. And from this sigma, I have this cross-entropy loss. And I got L here, let's say I call it L. So now I want to see what is parcel L, parcel O, let's say with respect to O first. Then we'll go continue to go backward. So parcel L, parcel sigma, let's see, will be a cross entropy loss, right? Okay, here I'm showing this part first. Right? Let's look at the parcel sigma, parcel O. So parcel sigma, parcel O here, so that's just a local gradient for this guy. So O is equal to sigma is equal to this one here. So let's look at the sigma I with OJ here. So take sigma I OJ here. I will just have let's see OJ here, right? I wait a sec. Oh yeah, okay. Here, like I split into two cases, right? So either I is not equal to J or like I and J are equal. So then I write sigma I O I here. So when I is not equal to J, then I have this one here is like exponential. This is actually OI here, right? Now OI here, exponential OK. Okay, here. So take the partial derivative of OJ here. So this one, like OI, of course, I is not equal to J. This is not, does not depend on this guy here, depend on OJ here. So, and here, like this summation, I will have a term that is equal to OJ, right? So therefore, I will have like exponential OI here. I pull out as a constant. And then this one here, I will have like I will basically have the sum, right? So this is like, I have some term here, like A, B, C, A plus B plus C. And I take derivative with respect to this guy here, with respect to A, let's say. I have like this square, right? This square. Then I will need to, if I take derivative with respect to O here, I will need to have also another term. What I mean is like, I will get back this term. Here I have square here. And then also I need to take the partial derivative of this sum here with respect to OJ here. And of course, for this guy, I will only get one term back. That's basically exponential OJ. So therefore, like I will have just have equal to this one here. And then it's very nicely. Then you see like I can group together. I can just like get back like sigma IO and sigma JO here, just two of them. And you can do the same thing, like if sigma I'll get something like this. So and I guess okay, this is just like okay, it's just algebra. I shouldn't bore you with this. So anyway, the interesting thing, if I go through the algebra, if you look at like partial L, partial O here, it's actually very intuitive. Like partial L, partial O will be just equal to P minus Q. If I say like Q is the ground truth and P is the Q minus P or P minus Q. Q minus P, yeah. So or Q minus sigma in this case. So and so if you have if Q is not the same as yeah, I'm already times up. I'm sorry about that. Maybe maybe next time I repeat a little bit of this guy and then we move on. So, okay, before we left, I guess one thing is important because you guys are submitting this uh, presentation, right? Presentation abstract, and we need to do a schedule here, just to roll to schedule like your presentation, and it disappear. Oh, okay. So I just do a lottery now. I will just do it once. So okay. I assume you guys are okay with these days here, and it will be like 2 weeks after it's more than 2 weeks from now, and basically you will have like we'll just pack like 2 presentation per lecture, so then you will have sufficient time to explain further. So but control your presentation not more than like 40 minutes, like 35 minutes, like something like that. So preferably like your presentation should be like around 30 to 35 minutes, and and okay, let me do this kind of like things like so this is the schedule. I will oops, this is not right, so I didn't change so I just want to have like 2% presentation per per day. So this will be the schedule. So uh
I guess you forgot my name.
is that yeah, I'm thinking it's like it's less than, yeah, it should be. So I'm missing one, right?
Yeah.
I I
Three,
don't know for some reason. Okay, like wait a sec.
three, four.
It's I didn't forget it. Actually, I pulled that from the one. I guess I probably did a bug in my code. Therefore, your name was not pull up. Let's see. I have 曾飞扬, right? 曾飞扬. Okay, 季凤阳, I guess. So okay, let's do it. I'm sorry for you guys. For those I used to have a good slot and become, but anyway, it's like within 2 weeks. So it's not a major difference, honestly. And you still have like more than 2 weeks to prepare, basically. Uh, and yeah, that's the schedule. I'm going to post on the web, and then like just prepare ahead of time. So I assume you will, because you're submitting your yeah, abstract this week. Yes, that's a yeah. I kind of like request you guys early because I I I I mean like it's not fixed. It's not that something like that fixed there. Like you can change, but um I really want you guys to start early to think about that. So put down at least like what you plan to talk about. But if the last minute you just want to change, it's okay. Yeah, project proposal also due like this week. Yes. Um and yeah, so yeah, it can be like it can be attribute format, but it doesn't necessary. Like you just need to have the oh okay. Abstract deal is not okay. I'm sorry. Like I probably mess up. So abstract deal like March 6th. Okay. So I didn't. So I guess I should change the date. So if abstract due March 6th, uh okay, but I are you guys okay with this day? Like maybe yeah, it's okay. Maybe I got 2 weeks. I maybe still maybe let's see if 2 weeks. Yeah, okay. Let's do it. Like it's okay. Like but actually, let's say still like March 6th is okay. I guess it's like still 10 days. It should be fine. So okay, we'll keep like this, and then like yeah, you just and by the way, like if you present going to present, let's say uh kind of I mean what do I say packages, so you may want to coordinate with other, but of course you won't know it until March 6th. Basically, if you submit like I will immediately post the topics I somewhere so that like you guys can look at like who is talking what, and then maybe you want to coordinate together. But I guess like there's so many topics that we don't have like many of us here. So if you if, in a very rare case, if like you have like six of like you trying to present PyTorch, then maybe probably you want to coordinate. Otherwise, I guess it should be fine. For example, if you have three guys, I do talk about TensorFlow, I think it's okay. So, but you will probably still want to coordinate a little bit so that you don't kind of overlap with the others. Like repeating like basically the same thing. And also like yeah, if you have taken my class before, I would like you guys to do a peer review. I will post some questionnaire to ask you guys to fill in. And your grade is mostly like for this part, like for the presentation, will be based on the peer review. So I will have my opinion, but my but my experience is that the crowd is usually wide, so I usually don't need to make any changes. Like so, uh, from like whatever you guys say, yeah. So I would yeah from the peer review basically. So okay, anyway, like that. Oh, and by the way, we have the homework assignment, new homework assignment as well. Just you want to take a look. Basically, it's doing like supervised regression. You can use packages like scikit-learn and try to play it with the same data as in the first homework. So okay, I will talk to you guys like later on then, like next week. See you guys next week, unless we have any questions. Okay, thank you. So I'm ending this now. Yeah, see you guys.